Welcome to part 2 of Swift Observation from Scratch. In part 1, we introduced the observation package, explored its behavior, and implemented a real stupid version of it, full of human error. Here, we'll incrementally replace the stupid, fleshy human parts with strong, perfect robot implementations. Terminating introduction in 3, 2, 1.7, 1.66666666666.
Okay, but that is just level 1, and it turns out that this on-change closure is not the sort of thread local state that is used. It's going to be a slightly different pattern, same general ideas and techniques, but let's see the limitations of what we've done so far. So one quick limitation is if I refer to multiple fields here and run this, the way it worked previously is that we would expect whichever property is first mutated will call this on-change callback and discard it. So this should only be run once, but if we run it now, we'll see that we actually run it twice, once for suspect name and once for suspect suspiciousness, which, if we remember how we store this thing, it's basically a map from any key path to callback to closure. Each key path gets its own copy, and each one will have to call and discard it separately. So that's a bummer, and maybe we could fix that doing something clever with our closure, maybe not just storing the closure, but storing some kind of closure with an ID. Anyway, it's not even worth considering that yet, so this is one difficulty. But the other difficulty that's going to be even more impossible to reckon with is if we have a second suspect here. Remember that we wanted any of these properties that are listed inside of this apply method, inside of this first closure, to trigger and discard the onChange. So this should really only run once, and certainly not 4 times. I've got to modify suspect to suspiciousness. So now if I run this again, we'll see that in our version, it calls this callback 4 times, which is not good. We want it to just call it a single time. If I go back and comment out our custom values here, our custom implementations, and run this, we'll see that it indeed prints out only once, not 4 times. And to solve this, our code is going to have to get a bit more complicated, which is why I wanted to at least establish these first patterns, because this is most of the magic. The rest is just dealing with these painful realities. So setting this closure state isn't going to be that great. If we think about the order of operations, first we set a global closure, and then we call apply, which internally is going to call access on various objects, suspect 1, access name, suspect 1, access suspiciousness, and it's going to do the same things with suspect 2. If each time we're grabbing this global closure and shoving it into some map, some dictionary, some form of storage associated with that key path internally, how do we ensure such that when suspect 1 calls that closure, that it removes the closure from suspect 2, and of course from suspiciousness? And this is going to be pretty difficult because we don't have all of the complete information. By the time we're calling apply, if we first set the closure and then expect apply to do this, by the time suspect 1's access is called, it doesn't even know that there is a second observable object in here. It doesn't have a lot of information to work with. And it's going to be difficult, maybe not impossible, but pretty difficult to solve this problem. We would have to really contort things by just storing a closure globally here. It was convenient, and I think the right next step in terms of complexity, so we can slowly lower ourselves into this steaming hot bath of involution, but it's not what we actually want to do. It would be way easier to solve this problem if instead we sort of inverted this a bit. Instead of setting a closure globally, maybe we can set some other kind of mystery state, and then when we call apply, we know that this access method is going to get called, and it can now reach out to this mystery state and do something with it. And then here, later on, after we call apply on step 3, let me actually move this up there. So in step 3, what are we going to do down here? We can use mystery state somehow, whatever this thing is, and potentially at this point associate the closure and perhaps give it the ability to cancel all callbacks, because at this point, theoretically, we would have known every single object and property, every key path that has been called in apply. So we have this global information that we can use to get the semantics that are required by this thing. So how can we possibly do that? We have a few requirements. One is that we want to store these callbacks on the registrar for each object. So suspect 1 and suspect 2 in this case would both need a callback, such that if each of these objects were deinitialized, we wouldn't want to leak this memory. We could store the callbacks in some global callback registry, but we'd have to be careful that when these things were deinitialized, we deinitialize those callbacks as well. And so storing the callbacks inside of these things, inside of the registrars, is a tactic we want to take. So we also want to create a new wrapped onChange closure, one that will call the initial onChange closure, but it will subsequently remove, using the global information, the callbacks from every associated object, and then take this new wrapped onChange closure and then stash it into the registrars of every associated object, which is basically a rephrasing of what I wrote here. In order to do these things, we'll need to know all of the associated objects and possibly all of the key paths that have been accessed in here. So we just need to gather this information. We want to roll a beautiful Katamari through this apply method. We want to create some form of state. It's like covering a bowling ball with beeswax and then rolling it through a field of tiny animals. And we're going to, at the end, pick up a very complicated and messy bowling ball that has all of the information. So what this actually is called is going to be an access list. At least that's what they've called it in the standard library. So we're going to make a struct called an access list. And then whenever access is called, it can reach out to some global access list. So I can just start by saying access list for our global access list. I'll actually prefix it with global. We'll have some global access list. Access will reach out to that access list and just attach the important properties, mainly itself and the key paths that were accessed. And access list can just gather all of that information, and we can use it at the end to stash everything properly. So perhaps access can call our access list, and maybe we can make a function called a track access here, which can take maybe the registrar itself, which will be some kind of observation registrar for suspect 1, for suspect 2, and then the key path that was accessed, so any key path. And this will be a mutating func that will change the access list somehow. Now, when we add suspiciousness for the same registrar, for the same object, we probably want to store these together. We could have just a list of tuples, but we probably want to deduplicate some of this noise. We could have also called suspiciousness multiple times, and we don't really care how many times we call this property. So perhaps a good way of storing this would be in a list of entries. Theoretically, for each observation registrar, we want to have a set of key paths so that at the end of this function, we'll have suspect 1's registrar associated with name and suspiciousness, and same with suspect 2's registrar. And if suspect 2 only called suspiciousness, then that would only have suspiciousness in here. Now, there is a problem. As you can see, this has given me some errors. I'm going to have to define a default value to get rid of this one. And then there's the problem that observation registrar does not conform to hashable, so we can't actually use this as our key. If this were a struct, we could possibly do it, but what the actual implementation does anyway is something like the following. Because this is a class, we can actually make something called an object identifier by passing this in here. And this object identifier can become our key, object identifier. And then instead of just putting a tuple here of any key path and observation registrar, which I think would work for our purposes, I'm going to make another type, which also exists in the actual implementation, called an entry. And I will put the key paths in here, and I will also put the registrar. And so this will be a map from object identifier, which is the registrar's ID, to an entry. And so the implementation for track access will be to reach into this entries, so entries for ID, which may or may not exist, so we can give it a default of a new entry, passing in the registrar, and then we can take the key paths and insert this new member. And with this implementation, we should have essentially the following code. We'll find the same entry, given the same registrar, and then we'll just keep appending key paths. So if we had some other field here, foo, and it was only accessed on suspect 2, well then that would be added here. So access would call into the global access list, passing itself in, its observation registrar in, along with the key path that was accessed, which would then either create a new entry in this entries list, or just insert a key path into an existing one. So at the end of the day, we'll have all the registrars that were accessed, as well as those key paths. Okay, so we're off to a decent start. So we are accumulating this information. We have our access list. Let me now go to access and have it call track access, because that's important. So I'm going to go up to access. Instead of storing this onChange closure like this, we're not going to do that. Instead, we're going to grab the global access list. And if this exists, we're going to track access with ourselves and the key path. And I didn't make this an optional value, but I want to. So I will make this into an optional access list. Great. So now scrolling back down, we have to set the access list. So here I'm going to set global access list equal to a fresh access list. And then we're going to call apply, which should add all of those properties to our access list. And then we're going to do some other stuff. But maybe here we can just print our global access list and see, have we done anything? And it looks like, yeah, it's hard to read this. So let me instead dump this global access list and make this a little larger and scroll up here. So our access list is a sum. It has this entries field, which is a dictionary of 2 elements, 2 key value pairs. The first one is some object identifier, and then it has a registrar, and then it has 2 keypads, suspect name and suspect suspiciousness. And then there's a second object identifier that has a similar 2 keypads. So that's great. Just to validate ourselves and make sure we're not crazy, let me just access name on suspect number 2 and just access suspiciousness in suspect number 1 and re-render, and we should see that we should still have 2 elements, one of which is going to access name and the other element is going to access just suspiciousness. So yeah, this identifier is for suspect 1's registrar and this identifier is for suspect 2's registrar. Cool. So we are collecting the information we need. However, we're not using it yet. None of our callbacks are being called. We're actually never even calling, or storing rather, this onChange closure anymore. But we now have our access list and we can use it as we please. And perhaps I can take our global access list and optionally call some other method that doesn't exist yet. And here I could now say register onChange. Let's say that, and I'll just pass it in this onChange closure. Of course, this method doesn't exist, but we'll let this method do the stuff that we talked about here. So up on our access list, we will make a new method called register onChange. This will take that onChange escaping sendable nullary function of void and do something. And I'll paste our notes above it. So now we have some entries to work with. So for each entry in entries, we can start there and think about this. Well, we have a couple of things. We have a registrar and we have some keypads. Let me just pull these out so we have everything laid out on the table in front of us. And so to some degree, we know we want to take our registrar and register once again this onChange itself on just this registrar. So we definitely want to pass along this onChange. And we also have all the keypads that we want to associate it with. So we can pass along these keypads at this point. Obviously, this method doesn't quite exist. However, this isn't perfect because this onChange, when it is called, will not remove from other entries this onChange callback. We have enough information to do it for a single registrar, but suspect 1 will not cancel the callbacks stored on suspect 2, or vice versa. We'll keep that in mind. Let's get this to work first because this is already a bunch of stuff. Not the full solution, but we can at least get it to work intra-key path cancellation. What a mouthful. So let's now go up to registrar and implement this method. Okay, so access is what used to be doing the storage of these closures, but now it's simply just logging the access to some global list. So now we want some other method called register onChange, and this is going to take a set of keypads, any keypath at this point, as well as that onChange. I'm going to just copy this because it's a mouthful, sendable closure that also has to be escaping, and that's going to do something. So with our very simple method before, there were a few problems. We could store these closures at keypads, but we could only store at most 1. That was definitely an issue. If we subsequently called with observation tracking, the most recent call would override previous closures. That's not great. We want to have lists of these or sets of these. And then similarly, when we actually call a closure, we want to be able to remove that same closure from other keypaths. So just to make that obvious, if I call suspect.name equals hello, and then suspect suspiciousness equals 1000. And previously I had tracked both suspect.name and suspect.suspiciousness. I would want this with mutation to call the callback associated with these two and remove the callback from both of them such that it was only executed once. So we registered here some callback, let's call it callback 1. This should trigger callback 1 and this should trigger nothing. This triggering, this with mutation, should simultaneously trigger the closure and remove it from other keypads. And we can think about what we need to do for this. Firstly, we need to be able to find closures associated with a particular key path. Well, we already have the beginnings of this. We can have a map from keypads to closures. We want to make this plural. That's okay. But similarly, once we find this closure, which we can find in here, well, just storing a closure isn't enough information because if we mutate name, we don't necessarily, at this point, know what other keypads had that closure associated with it. Whatever value we get back here needs to be able to link us back to all of the keypads that it was associated with so we can search for it and remove it from whatever storage we were using for those. So in order to facilitate this, these closures need some form of identity, which normal closures really don't have, shouldn't have. So we're going to make another struct, and this is called an observation in the actual implementation, so I will steal that. And basically this is going to have an ID. So this observation has an ID. It's going to have some key paths. This will be a set of any key path. And then finally it has the actual closure, which will be, once again, sendable unit to void. Great. So this registry, let me make this identifiable just for fun. This registry will now be a map, a dictionary from any key path to observation IDs, in fact, a set of them. So we might add multiple onChange callbacks to the same key path, subsequent calls to with observation tracking with different properties. So we want to create a second closure and associate it with suspect name. And then when we call suspect name, we want to be able to call both closures. And similarly, if we call suspiciousness, this should find and trigger callback 1 that was associated with both properties and remove just callback 1 and not callback 2. So this notion of identity is going to be very important. Okay, so we're storing this set of IDs, but then we actually need to store the observations themselves, which I'm going to make a map from its identity to the actual observation type itself, so we can look it up quickly. Now in the real implementation, there isn't a UUID in here, it's just ints and ints, and then this registrar has a ID field that it increments and has a function for getting the next ID, just incrementing them, monotonic ID for this thing. Maybe this is slower generating a UUID, but I find it a little clearer than just seeing sets of ints here. Okay, so now maybe we have enough to do everything we need for registering an onChange. So the first thing we need to do is create a new observation. So I'm going to make a new observation, and it simply takes the key paths and the onChange closure. That's pretty great. And then we need to store it off in a couple of these maps. So this should be easy. Observations of observation ID will equal the observation. And then registry is going to be a little more interesting because basically for each key path, we're going to take this registry key path and insert the observation ID. Now this is optional, right? Maybe it's the first time we've added any observation to this key path, so we'll have a default of an empty set, and then I can remove that question mark there and rebuild. So this is looking good to me, but there's a failure below, and the problem is now we've broken with mutation. These both need to work in tandem. We've just set up this first part of registering these changes, setting up this registry and these observations, and this registry is actually, I can give this the real name. It's called lookups on the actual implementation, at least today. So we can look up a set of observations, a set of callbacks for any key path. Naming is hard. Okay, so now we're setting this up, but now when we actually mutate one of these values, we need to find the corresponding observation and then be sure to remove that observation from any other key path lookups so that we don't call it again later on. So let's go down here. Okay, so the first thing to do is to look into our lookups, which takes a key path. And what this is going to do is get us back a set of observation IDs. So there could be 0 observations, 0 callbacks associated with this key path, or potentially multiple. And let me actually pull this up to where we had our notes so that we can just keep those in mind. So name, for instance, would have both observations 1 and 2 associated with it. And then for each observation ID, in observation IDs, we want to find the associated observations. So if let observation equals observations observation ID. So now we're finding the actual observation value that has been stored up here. Let me move some stuff around so we can just get as much onto the screen as possible. So we're now finding one of these. The first thing to do, or one thing that we can do, is actually call the closure. That's something we wanted to do. We've called the closure. We've let everybody know what's going on. But then, once we've done that, we need to look into each key path that the observation was associated with. Once again, the concrete case would be here. We have, say, called name, modified name. Therefore, we want to find both callbacks 1 and 2, observations 1 and 2. And for callback 1, this observation was associated with multiple key paths, name and suspiciousness. So now, after calling this callback, we need to find suspiciousness and remove its ID from suspiciousness's set of observation IDs. So now we can say lookups at key path, and we can remove the observations ID. Now another thing we can do here is the initial key path. When we're looking this up, we can wipe out the set of observation IDs. We don't need those anymore because they should only be called once. So instead of using subscript, we can say remove value for key paths. That will simultaneously get us the value after dumping it out of the dictionary. And that's a lot of stuff. This was level 2. I'm now going to run the code, and we're going to see we have half the number of callbacks as we did previously. Let's go back to what we were actually running to remind ourselves. So we were observing two different objects, and we didn't quite solve that case, so let me remove suspect 2 temporarily, and let's see if we solve the first complication, which is that we have associated this callback with two different keypads. So I'm going to run this and scroll this all down a little bit, and we'll see that this is only ever called once. I'm actually going to make this really big. Callback is being called. Yay! And so it doesn't matter what order we call these in, it's only being called once. So we're successfully disassociating this callback after calling it. And maybe we can just actually take a look at what's going on. Let's step through this code. I'm going to throw in a breakpoint, let's see, here. Then I'm going to throw in a breakpoint at access. So now I'm going to run this code one more time with these breakpoints, and let's step through and see what's happening. So we are currently in here in observation tracking, and we've called name the first time, which means we've called the name getter, which means we've called access, which means we've called access again nested, and now we're just printing out this value. So then we're going to look into our global access list, which does exist. It was set previously at the beginning of with observation tracking, though it is completely empty. And then we're going to call track access on that. So I'm actually going to also throw in a breakpoint there. So when I hit fast forward, we should just jump right ahead. And so now we're calling on suspect's registrar with the key path for name, suspect name. We're calling track access on our access list. So we're going to first create an identifier, this object identifier thing, which is not very interesting to look at, but it will be unique and constant for suspect 1. Then we're going to update the entries. So these entries are currently empty, but once we execute this, we'll see that entry has one key value para on it, going from suspect 1's object identifier to an entry that stores the registrar and the name. So that pattern's just going to keep continuing with every access. So let me fast forward. So now we're in access a second time. This time we're in that same closure calling suspiciousness. So we're calling suspiciousness as getter, which is calling access with its key path, which is calling access on a registrar, which is calling access here, which is going to drop into track access, creating another ID, updating the entries, which now, if we observe one more time, has two elements, or rather one element in the overall entries map because it's the same object, and this has two key paths stored inside of it, suspiciousness and name at this point, which is great. Okay, so next we're done with apply. We've walked through these two accesses, and now we're at register on change. So let's dive into this. We're finally calling on our access list register on change, passing in our closure. So now we're in here, and now we're going to iterate through our entries. So let's do that. The first entry is going to be the only entry, which has those two key paths. So we have our suspect 1 registrar and these two key paths. So key paths are, once again, suspiciousness and name, and then we're going to call register on change on our registrar. Diving in here. So now with all of this information, we can create a new observation, and now I'm rhyming. So this observation that we've created has its own unique UUID, which would just be a monotonically increasing int in the actual implementation, but it's nice to have this here. And it has all of the elements, all of the parameters, the key paths that were associated with this observation that should trigger the execution of this observation. And it has the actual onChange callback it needs to call. And so now on self, we have this empty lookups map and this empty set of observations. So the first thing we're going to do is modify this observations map. So if we look at our map now, we'll see it has one element where we've stored this observation at its ID. That's great. And then for each of the key paths, so two of them, the first one would be suspiciousness, we're going to insert that into lookups. So let me run through that. We'll see what lookups is now after the first iteration. It now has suspiciousness pointing to the ID of that observation, and we're going to do that again for the second key path, which is name. And once this is run, lookups now has two values. So when one of these is mutated in just a moment, we can now find the correct observation and then call it and cancel it. So let's keep moving. So we finished with register on change. We finished with this. We can now return our result. And now we're beyond with observation tracking. And here we go. Let's move down to suspiciousness. We're modifying this, so let's jump into this. We're calling the setter, which means we're going to call with mutation, which means we're going to be calling the registrars with mutation with the key path of suspiciousness. And if I dive in here once more, we're going to print that we're mutating this, and now we're doing this bit of logic. So first, we're going to go into lookups and take all the IDs that have been associated with that particular key path. So let's move beyond this. So we've gotten that single observation ID because we've only ever registered one observation. And now we're going to go through each of these IDs, which there's only one of at this time, of course. And we're going to find the observation, which we do. There it is. We print it out. There's our observation with two elements. So the first thing we're going to do is call its callback. So we should see printed now. Callback is being called. There we go. And then it's just a matter of some cleanup work, where we move through each of its keypads, removing the corresponding observation ID from its lookup. If we take a look at lookups now, well, we've already removed one of those elements. So previously suspect name was pointing to this observation ID, but also suspect suspiciousness was, but because we are calling this for suspiciousness, this line has removed that entry already. So now we need to clean up all of the other references to that observation so that we never call this closure again. So now that we've gone through with both keypads, we can look at our lookups and we'll see that, well, suspect name still exists, yet it has no elements. And this means we can actually do one last cleanup, which we can see if lookups at keypath, if this is empty, and which is actually optional, so it's a little awkward to do this. I will say empty or, well, false. If it just doesn't exist as well, I have to account for that. Then I can say lookups remove value for keypath just to clean that up, which I didn't do. It's still here with no elements. Another thing I realize now is that this observation is still hanging around despite the fact that we've called it and we'll never call it again. So we could also remove value here in just the same way for key observation ID, just to do some more cleanup of these little dictionaries that we're using for our state. So I'm glad I stepped through that. And now we can just keep walking and we're basically at this point done. Yeah, we've made it. When we modify a suspect name, later on it would go to with mutation again, but it wouldn't find any associated observation IDs. So it would just stop progressing. And that's all pretty cool. We have solved a fairly nuanced challenge. Now, the final piece of this puzzle, if we want everything to work as it does in the actual API, would be getting this to work. And we're actually not so far off from doing it, so let's just take it all the way. This should only be called once. And this is interesting because now we want this inter-object, this inter-registrar communication. If this callback is executed, if this observation is found and executed inside of suspect 1, we wanted to cancel not only the observations tracked for its other keypads on the same object, but also on the tracked keypads on other observable objects in this same closure. So let's think about how we could possibly do this. Let's scroll up to here. So this is where we've collected all the information. We have all of the registrars. We have all of the keypads. And now we can register on change. So inside of our access list, we care about this method. So we haven't quite done this step, which is to create a new onChange that will not only call the initial onChange, but somehow has the power, using all of this information at this point, to deregister the observation from every other registrar. And there's going to be this interesting chicken and egg problem. Well, let's take a look. Here I'll say canceling onChange. And this is going to once again be a sendable closure. And what we're going to do is we're internally going to call onChange. That needs to happen. But we also want to cancel the observations on every registrar. So in this closure, we want to cancel observations that will have been registered here, where we're passing in the closure. So this is another one of those head scratchers. How do we do this? How do we square the circle? We are going to once again turn to mutable state. Inside of here, we need to cancel the observation. So let's do that. We have every registrar. So I'm going to say for entry in entries, and then I'm going to say entry, value, registrar. And now that we have the registrar, we can say cancel. The question is, what do we cancel it with? We want to cancel it with some kind of observation ID. And for that particular registrar, actually. So we'll need some kind of information. We'll need to know the observation ID that we won't know until after we've already called this. So what we're going to do is actually create some piece of state here and call it observation IDs. And this is going to be a map from those object identifiers. This will be each registrar's identifier to a registrar observation ID. Now it's pretty nested, so that's awful looking. And we're going to just make an empty map here. And say this existed, how might we solve this problem? Now in here we can say for every ID or every registrar ID, observation ID in observation IDs, we can get the entry for this, which has a registrar on it, and then we can cancel this observation ID. Now that's a problem because this registrar doesn't have a cancel method, but that's okay. Let's implement a stub version. So I'm going to scroll up into our observation registrar and just quickly throw in a cancel func that will take in an observation.id, and this will do something, should cancel observation ID. And then we'll scroll back down. And now we've gotten this other more perplexing issue, which is that we've, well, referenced a captured var in concurrently executing code. So remember that this needs to be sendable, yet we've just thrown a reference to this in here. So we've already vaguely mentioned this problem before. The registrar itself in the real code is a struct and not a class, and we simply made it a class to get around some problems. this is a similar version of the same issue. And Swift actually deals with this by creating this box structure that mediates access with a lock. I think I've mentioned this before, but here we'll actually need something. It won't be an actual locking implementation, but we can get around this problem by creating a little box type here, a box of A, which will store a variable value of A. We can initialize this with an A here. And now we can take, instead of just having observation IDs, we can have a box of this map and just wrap this inside of a box. And now here I have to say observation IDs.value. And so we've passed this reference type along. And so Swift is trusting us that we have made this box concurrency safe. It's kind of up to us now to ensure that this is safe to share and send. It's not. Now we're lying. But in the real version, whenever you tried to modify this value, there would be a lock that would lock and then unlock in a defer clause. We can look at that in the future, but now we actually do need some version of this just to get this code to work, to deal with the fact that this has to be sendable. So now we have this box, this mutable box that we're going to store the observation IDs that would have been registered for this particular observation for each registrar, and we can iterate through these and then find the corresponding registrar and call cancel inside of this onChange callback that we're going to be passing along as this decorated onChange callback that will be executed whenever anyone mutates any of the values, the keypads on any of the registrars. So now the problem is we've never actually set this to be anything. This will always be empty. So one thing we can do is register onChange actually can return an observation ID. And then in here, we can take this observation IDs and we can grab the value and we can add our entries key, which is that registrar's ID, to be equal to the observation ID. Now the problem is that this isn't in fact an observation ID, it's unit, because this doesn't return an observation ID, but we can fix that trivially by saying, well, this should return observation ID. And we'll just return at the end here, observation.id. And now the build succeeded, and let's see if we've messed anything up. So the grand reveal, this should really only call this callback a single time. And it called it twice, but that's because of this all caps message here, because I forgot to implement cancel. So let's scroll up one more time. So remember, we're calling here cancel with this observation ID. And if this actually were implemented, this might have worked. So let's scroll up to cancel. And so what should this do? Well, this should do something very similar to what we had inside of with mutation, in that for this observation ID, we need to remove it from observations, and then for each key path, we need to remove that value. So really we can just copy paste this, and I will say cancel this. Let me build. Great, and now that we have abstracted this, what do we want to do in here? We want to, I guess, cancel this observation ID. That will clean up that code slightly. And so now if I rerun this code, I'm hoping it should work, but it didn't quite exactly, but we sure see that cancel is being called a lot. So we have a little bit of debugging to do. Let me just make sure it works with a single call. So callback is being called just once, but when we call it twice, it's still being called twice. So let's see why that is the case. And looking at what we've just done, I see the problem. I preemptively did some refactoring that doesn't really make any sense. Inside of cancel, I'm calling the observation, which is very silly. And so instead of doing this, I'm going to simply undo that refactoring, and I'll keep this as it was for now, and I'll just remove the actual calling of that closure here. So here we're going to call the closure, here we're not. We could refactor this to make it nicer, but that was disturbing for a moment. If I now save and run this code, callback is being called only once, and we've made it to the end. That is truly pretty complicated stuff. It took a while to work through the open source code and figure out the flow here, but it's working. It's pretty much doing what we've looked at the beginning. We haven't handled every edge case. We haven't handled nested calls to this, but that can be an extension if you feel like trying to think about what it takes to get something like this to work properly with the semantics that we observed at the very beginning. That would be a fun challenge, but I think you sort of can start to see the patterns that we've worked with here. And just to reiterate one last time, because we've written a good deal of complicated code, what's happening is at its core simpler than all of this tracking. We needed to do a lot of bookkeeping to satisfy every single constraint, but really we're calling this with observation tracking method, which is passed to closure. Closure calls these special decorators that have been added by a macro, which reaches into some thread local state, tracking keypads and tracking these associated repositories, these registrars for holding on to these closures. Once we've called that method and therefore gathered in our access list all of those keypads for their associated objects, we finally associate that closure with each of those objects. But we have to do one little tweak, one little bit of decoration here, which is confusing looking, where we need to make sure to be able to cancel this closure on other objects. So we need to store off this value that will gather all the observation IDs, create this decorated closure, and then finally associate that decorated closure with each observable object for each key path that was observed on that observable object. And that's crazy. That's cool. It's complicated, a lot of back and forth, but at the end of the day, yeah, it makes sense, I think, sort of. I hope that was a fun journey. Let me know if there are any aspects of this you'd like me to explore more. I'd love to go into things like what I kind of hand-waved about, which was more of that thread local. How does it deal with that? How does that work? Locking, how it actually implements this concurrency safe box. Nothing we've done here is actually concurrency safe. So these details of the actual performant real implementation are super fascinating, but they add more and more complexity. I hope this was a nice deep dive. I will add links to this code base as well as the actual open source code where you can now hopefully get a good sense of the real stuff, the real deal, which is a little more complicated than this. It does some more stuff and has slightly different naming. I tried to use as much of their real naming as I could, but I found some of it to be a little confusing, so I tried to simplify it here and there. Yeah, until next time. Bon voyage.